All right, so the last thing that we're going to do with the series notes is the alternating series test. So you're going to like this one because it's pretty straightforward. Anyways, an alternating series is a series whose terms are alternately positive and negative on consecutive terms, right? Positive, negative, positive, negative. And remember that if you're given the series written like this, you can see it right away that it's negative, positive, negative, positive. Or if you're given the series in sigma notation, you know that this part right here lets you know that this series is going to be alternating. Another form is negative 1 to the n. That is going to be alternating. So in general, just knowing that the limit as n approaches infinity of a to the n equals 0 tells us very little about the convergence of this series. However, it turns out that an alternating series must converge if its terms consistently shrink to 0. So this is what the alternating series tells us. First of all, alternating series only tells us that it converges. It doesn't tell us anything about divergence. Other tests we use for divergence, and you'll see what I mean in a second. All right, if a to the n is greater than 0, then the alternating series, and the reason we know it's alternating is because of this part or this part. This is the alternating part. Which tells us that we can use the AST, or the alternating series test. These converge, if both of the following conditions are satisfied. That means if you take the limit as n approaches infinity of just the a to the n, okay, just the a to the n part, which means without the alternating part. The alternating part tells us to use the alternating series test, but we're going to use the nth term test and see if it equals 0 just for the a to the n part. Okay? And you'll see what that means in just a second with examples. And of course, a to the n is decreasing or not increasing sequence. That means this sequence has to be decreasing. For example, you start at 1, you go to half, you go to 1/3, you go to 1/4, okay? And here you start at 1, you go to 1/2, you go to 1/6, you go to 1/24, and so on, for all n greater than k. All right, a big note is this does not say that if the limit as n approaches infinity of a to the n does not equal series, the series diverges by AST. But what we can say, if this happens, if it does not equal 0, we can say that the series diverges, but not by AST, but by the nth term test. Okay? So the AST can only be used to prove convergence. You can't say diverges by AST. Okay, that doesn't work. So look at the following examples. Okay, now the reason that we're going to use the alternating series test is we have the alternating part, right? So really quick, what I'm going to do is I'm going to identify all of the alternating parts in all of these problems. Some of them are pretty easy. So there's the -1. So that right there is my alternating part. -1 to the n is my alternating part. You can't separate the +1 from the n, right? So this whole thing is your alternating. Cosine, we know, is an alternating function between -1 and 1, right? So this whole thing is going to be my alternating part. -1 and -1, that's my alternating part. -1 to the n and -1 to the n plus 1. The reason why it's important to identify the alternating parts is because we are not going to include those in our little conditions. Okay? So once I've identified that this is my alternating, I'm going to test using AST, alternating series. And remember, the first condition means that the limit as n approaches infinity of just the a to the n part, so without the alternating part, which is n over 2n minus 1. This equals, because we have dominating terms, it's 1 over 2. So obviously this does not equal 0, right? So we can't say that it diverges by AST, but what we know is because 1/2 does not equal 0, it diverges by the nth term test. Okay? Next one. We know it's alternating, so I'm going to start with my first test. I'm going to see the limit as n approaches infinity of just the a to the n portion without the alternating portion, which is n to the ln of 2n. Obviously this is infinity over infinity, so this is an indeterminate form, so we must use L'Hopital's rule, which is 1 over 2n times 2, and that just simplifies. The 2's are gone to 1 over n, which remember is 1 times n over 1, and that's just n. And when you plug in your infinity, that's infinity. Does that equal 0? No. So this diverges by what? By the nth term test. Okay, next up, we've identified the alternating part, cosine. So this is just going to be the limit as n approaches infinity of 1 over n. And that's just going to be 1 over infinity, which is 0. So check. Okay, so check means that it satisfies the first part, that the limit as n approaches infinity does equal 0. So far it converges by AST, but now we got to make sure that this is decreasing, right? That it's a decreasing sequence, and it is, because when you plug in 1, it's 1. When you plug in 2, it's 1/2. When you plug in 3, it's 1/3, and so on and so forth. So it satisfies both conditions. So this converges by AST. Okay, this is almost identical to this one. So the limit as n approaches infinity of 1 over n factorial. And this is just going to be 1 over infinity factorial, which is just 1 over infinity, and that's 0. And it does converge by AST. And it does satisfy the second part, because as you plug in your n values, this does get smaller. Alright, next part. Here's the alternating part, so I'm not going to include it. So I'm actually just going to do the limit as n approaches infinity of 1 over n minus 5 squared plus 1. And that's just going to be 1 over infinity, which is 0. So it converges by AST. And then the last part is easy. It also converges by AST. Okay, you guys finish that one on your own. Alright, now there's two different, for alternating series, we have two different types of convergences. There's an absolute convergence versus a conditional convergence. Alright, if the series, absolute value a of n converges, then its series without the absolute value also converges. Such a series is called absolute convergence. Notice that if it converges on its own, the alternator only allows it to converge more rapidly. Okay, and I'll explain what this means in just a second. Now, if the series is conditionally convergent, then the series without the alternator converges, but the series with the absolute values diverge. Now, what's important about this is to follow a series of steps. Now, here are the problems say determine whether the following alternating series converge absolutely, if they converge conditionally, or if they diverge. So really quick on the side, I'm going to tell you guys the rules. The first thing that you always do is you test absolutely first. And after, the way that you do this is after taking the alternator out, use one of the other tests to determine convergence. Okay, and I'll show you what that means in just a second. Now, if this converges, then you're done. Then you can say, all right, it absolutely converges. Second, we use, if this diverges, you have to then now test for conditional. Okay? Conditional convergence means that it only converges if we use the AST. So we're going to use the AST to see if it converges conditionally. And then, of course, if both of these diverge, then you say that the whole thing diverges. Okay? So here's what I mean. So here is my alternating series. The reason I know it's alternating is because this is my alternating part. So here my A of n is actually just going to be 1 over the square root of n, correct? After I remove the alternating part. I'm going to rewrite this because as soon as I rewrite it, you'll notice which test you should be using to test this. So my new series without the alternator looks like that. What test would you use to test that series? Okay, if you said the p-series test, you are correct. So we're going to use the p-series. What is my p here? It's 1/2. And since 1/2 is less than or equal to 1, we know that using the p-series, it diverges, right? By the p-test. But we're not going to stop here. This just proved that this guy does not converge absolutely. It doesn't converge every single time. Now we're going to test, does it converge conditionally? And remember, what did I say? What do we use to do the conditional? We're going to use the AST for conditional. And for AST, we remove the alternator and we test, does the limit as n approaches infinity of 1 over n to the 1/2, does it equal 0? And it does. Okay, it's 1 over infinity, which is actually 0. So because it does pass the AST, we say that the series, so this series right here, converges conditionally. Okay? It does not converge absolutely. Okay? All right, next one. Here's the alternator, the alternating part. So I'm going to rewrite this series without the alternator. And what does this look like? If you said a geometric series, you would be correct. So we're going to use the GST. And the GST, we're going to use the common ratio, which is 1/3. And we're going to ask ourselves, is the absolute value of 1/3, is it less than 1? Yes, it is. So, using the GST, this converges. And since it converged from the first test that we used using other than the AST, we can say this converges absolutely. Because what this tells us is that if it converges using GST, the alternator, so if I was to have this in here, it only allows it to converge more rapidly. Okay? All right. The last part, alternating series remainder. Let's leave this and do it tomorrow. But just to set you guys up, you read what this says right here. And we are still going to be removing the alternating part. And if you go backwards a little bit, what is S of 6? Okay, so write this out. That means the first term, when n equals 1, this is going to be 1 over 1, right? So 1. Now, the alternator only tells us that our next term is going to be a negative, and it's going to be 1 over 2. Then we're going to have 1 over 6 minus 1 over 24 plus 1 over 120, 720. Nope, 120, sorry. Minus 1 over 720 plus 1 over 50, 40. I know that these right here are 7 terms, but you'll understand why I did 7 terms when you read this statement. So try to start it off if you can. If not, leave it. We're going to do this tomorrow in class together. All right, enjoy.